I'm Dr. N.B. Hulle. In this video, we will try to understand the analysis of transient response of the RC series circuit, that is the first order system. In this case, we will try to understand the behavior of the RC series circuit with source before switching and after switching. That is source driven with some initial condition, and its detailed analysis we will discuss further. Now here in this case, for the analysis of the transient response of the first order system, that is RC series circuit. This circuit consists of the two sources, which is V1 and V2. One source exists before switching and another source exists after switching. Now here in this case, we have the two positions. This is the switch position 1 and this is the position 2. Circuit switch is in position 1 and circuit was reached to the stable state. In that case, this capacitor behaves as an open circuit and this V1 is a source connected in the circuit. Now, we will analyze the circuit in the two different situations. That is, one is for t less than 0, that is before switching, and another is for the t greater than 0, that is after switching. Now, in before switching case, the voltage V1 is available in the circuit. This resistance R is also available in the circuit, and this capacitor was in the steady state or in the stable state, and it is represented by the open circuit. Now here the voltage across capacitor is same as the applied voltage, which is V1. That's why Vc of 0 minus is equal to Vc of 0 plus is equal to V1. This is the analysis of the circuit for t less than 0. Now we'll try to understand the behavior of the circuit for t greater than 0. And here in this case, for the t greater than 0, again after switching, source V2 is existing in the circuit. This resistance is R as it is, and this is the C is the capacitor, and we are trying to understand the transient behavior of the circuit. By the KVL, for that purpose, we will mark the polarities here. This is the positive terminal of the voltage across resistance. This is the positive terminal of the voltage across capacitor. This is the negative, and these are the positive and negative terminal of the battery. If we are traveling in the clockwise direction from this particular point while applying the KVL, if we are traveling in the clockwise direction, negative to positive, that is a plus, its voltage which is V2, then positive to negative, which is minus, voltage across resistance is I of t into R, then positive to negative, which is minus the voltage across capacitor, which is Vc of t. Now here in this case, voltage across this capacitor, we will assume its value as Vc, or sometimes it can be represented as Vc of t. Now here in this case, we are representing this value as Vc of t, and which is equal to 0, because after that there is no element in the circuit. But here we know that the current flowing through the capacitor is raised up change of charge, that is dq by dt, which can be represented as I of t is equal to C into dv by dt. This I of t is replaced by C dv by dt, which is nothing but d Vc of t upon dt. In that case, this V2 will be the same, this resistance R will be the same, and this I of t is replaced by C into dVc of t upon dt minus this value, which is Vc of t, which is equal to 0. We will simplify this equation value and this value to the RHS. In that particular case, V2 is equal to RC into dVc of t upon dt plus it is Vc of t. Now we are using we want to use the integration. For that purpose, we are using the variable separable method. We are separating the variables. Now here it is V2 minus this value, that is Vc of t, which is equal to RC into dVc of t upon dt. If we are further simplifying this particular equation, in that case dVc of t upon V2 minus Vc of t, which is equal to dt upon RC, and if we are integrating this equation on the both sides, we are able to get its solution. In this particular case, the differentiation of denominator is minus 1, and if the differentiation of the denominator is available in the numerator, then log of denominator will be the integration of this left hand side term. That's why we are multiplying by the minus sign, because its differentiation of the denominator is minus 1. In that case, minus 1 we are multiplying on the both sides. Now the differentiation of the denominator is available in the numerator. That's why log of V2 minus Vc of t, which is equal to, it's 1 upon RC, that is minus 1 upon RC is the constant, integration of the dt is t plus some constant of integration, and we will name this equation as equation number 2. Now we can find out the value of the integration constant from the initial conditions of the circuit. Now here initial condition of the circuit in this particular case at t is equal to 0, Vc of 0 minus is equal to Vc of 0 plus is equal to V1. Now we will put this value in the equation number 2. In that case, this is log of V2 is the constant, and this Vc of t or Vc at t is equal to 0. This value is V1, and at t is equal to 0, this value will become 0, and this is the k. And from this equation, we are able to get the value of the integration constant, which is k, which is nothing but it is log of V2 minus V1 is the value of the integration constant. Now, we will put the equation number 3 in equation number 2. That is, this k is replaced by this particular value, then we will get the next equation. Now here, if we are simplifying this equation further, or we are putting the equation number 3 in equation number 2, in that case it is log of V2 minus Vc of t, which is equal to minus t upon Rc, plus it is log of V2 minus V1. Now if we will shift this value on the left hand side, then it is log of V2 minus Vc of t minus it is log of V2 minus V1, which is equal to minus t upon Rc. We'll use the formula here, log A minus log B, that is log A upon B, that is V2 minus Vc of t divided by V2 minus V1, which is equal to minus t upon Rc. We are taking the antilog on the both side. In this case, this log and antilog will cancel. This term on the left hand side will be V2 minus Vc of t divided by V2 minus V1, which is equal to antilog of this term will be e raised to power of minus t upon Rc. Now here in this case, this Rc is the time constant, which is tau. That's why here V2 minus Vc of t divided by V2 minus V1, which is equal to e raised to power of minus t by tau. If we will simplify this equation, this numerator will be V2 minus Vc of t is equal to, that is V2 minus V1 into e raised to power of minus t by tau. In other words, this Vc of t is equal to, that is V2 minus in bracket V2 minus V1 into e raised to power of minus t by tau, and this will be the final equation, that is equation number 4, or expression for the voltage developed across capacitor whenever the source is existing before switching as well as after switching. This V1 is the voltage source existing in the circuit before switching, and this V2 is the voltage source existing in the circuit after switching, and this tau is the time constant of the circuit after switching. Now here in this case, the same equation can be generalized, that is Vc of t is equal to V minus V naught inside the bracket into e raised to power of minus t by tau, where this V is the voltage available in the circuit after switching. This V naught is the voltage available across the capacitor before switching. Now we can use this equation in the two different ways, because whenever the source is existing in the circuit before switching and after switching, the same will depend whether the charging of the capacitor is taking place or discharging of the capacitor is will take place, depends on the value of V1 and V2 or the value of V and V0, that is available voltage in the circuit before switching and after switching, that we will try to understand here. The general equation for this case is Vc of t is equal to V minus inside the bracket V minus V0 into e raised to power of minus t by tau, where this V is voltage available in the circuit after switching, and this V0 is nothing but the voltage available across the capacitor before switching. Now here in this case, if V2 is greater than V1, that is nothing but this V is greater than V0. In that case, the expression for this Vc of t will be V minus Vx into e raised to power of minus t by tau, because this V is as it is. Then here in this case, this V minus V0, in this case this V is greater than V0, that's why this subtraction will be the positive, and that subtraction is a Vx, this minus sign as it is, and e raised to power of minus t as it is. Now we will substitute value, or we will calculate the value at t is equal to 0 and at t is equal to infinity. If we are finding the value of the voltage across capacitor at t is equal to 0, if we are putting this value 0 in this particular case, this t is 0 means e raised to power of 0 is 1, that is V minus Vx. V minus Vx is the voltage available in the circuit or available across the capacitor at t is equal to 0, which is this value V minus Vx. In this particular case, V minus Vx is the voltage available across the capacitor at t is equal to 0. Now at t is equal to infinity, we will find out the similar value if this t is equal to infinity, e raised to power of minus infinity is 0, 0 into this Vx is 0, and this value, resultant value will be V minus 0 will be the V, and this is the maximum voltage available in the circuit, that is at t is equal to infinity. Now here in this case at t is equal to infinity, this instant means in this particular case the voltage across capacitor will increase from its initial value, and initial value is V0, which is same as voltage V1. That's why it will increase from voltage V1 to its maximum value. That's why, unlike in the previous case, because when we have studied the source driven RC circuit with zero initial condition, in that case this graph was something like this, and it is going to the maximum value. But here in this case, initial charge is existing on the capacitor, which is nothing but V1, and this value of the V1 is nothing but Vx here, which is V minus V0 is the initial value of in that particular case. Similarly, if we will try to understand in this case, if V1 is greater than V2, because the same is the equation, Vc of t is equal to V minus in bracket V minus V0 into e raised to power of minus t by tau, and if V1 is greater, means in that case the voltage available across the capacitor before switching is greater than the voltage applied across the capacitor after switching. In this case means V0 is greater than V. In that particular case, this subtraction will be the negative, and into minus this sign, that value will become plus. That's why this V will be as it is. This V minus V0 is suppose Y. This value will be the plus, and e raised to power of minus t by tau. Now here in this case, we will find out its value at t is equal to 0 as well as at t is equal to infinity. This Vc of t at t is equal to 0. At t is equal to 0, this value will be the e raised to power of 0, that is 1. Means V plus By will be the value of the voltage available across the capacitor at t is equal to 0. And finally, at t is equal to infinity, in that particular case, e raised to power of minus infinity will be 0, 0 into Vy will be 0, this Vc of t is equal to V, and this is available voltage is V. This is the value at t is equal to 0. Means at t is equal to 0, we have the voltage V plus Vy, and at t is equal to infinity, we have the voltage which is V. In this case, the voltage before switching is higher value and voltage after switching is lower value. There is a possibility of the discharging of the capacitor, but this capacitor will not discharge to its zero value as we have discussed in the source free case, because in this case after switching also some finite voltage is available in the circuit, and same amount of the voltage is available across the capacitor. Below that value discharging is not possible. That's why in that particular case the capacitor will discharge to its minimum value, which is nothing but the V, and that is the case of the transient behavior of the circuit whenever we have the source is existing before the switching as well as source is existing after the switching. Finally, the transient response of the first order system, in which we are also interested to calculate the current flowing through the capacitor, which can be calculated by using the equation, that is C into dVc of t upon dt, and voltage across resistor we can calculate by using the formula R into I of t into dt. The similar formulas we will use. That's it about this video. Thank you for watching this video. That's all.